So let's shift our discussion from two charged species to two uncharged species. This is called van der Waals forces, VDW, and there's a class of, this is three of them that are embedded within van der Waals forces. And again, these are two non-charged species, so just dipoles, or maybe things are not even dipoles. So let's look at two things that are dipoles. So as I showed to you just before, when you have two things that have poles, you know, like water, we said, had a positive pole and a negative pole. Let's say it's seeing another molecule that also has poles, positive and negative, because there's an electronegative portion here and a less electronegative portion here. It will have a pole. They reorient themselves so that the positive and the negative interact because they're attractive. And this is known as dipole-dipole attraction. Okay, also known as Keeson. This is just your enrichment. And it's of the van der Waals, it's the strongest, but it's still weaker than ionic. Okay. Sometimes there are molecules that don't have poles. Okay, they just don't. So they're non-polar molecules. Okay, so what happens when a polar molecule sees a non-polar molecule? That, you know, that's a question. So for example, when we talked about chapter 9, we talked a whole bunch about non-polar molecules. And for example, where methane, CH4 methane, was non-polar. It was symmetrical, it was tetrahedral, and so all the different sides collapsed onto themselves, and there was no one area of the molecule that was more positive or more negative than the other. So what happens when it sees a polar molecule? Well, this molecule will induce a dipole in the neutral molecule. It will make it so that the charges align themselves inside so that the positive and negative attract one another. Okay, so it will effectively do this. And this is called polarizability. It will polarize the molecule. Okay, so it's polarizing it, so now the positive and the negative face one another, and they're attractive. And large molecules, large purples, can induce more easily. Okay, so the force between a dipole and a non-dipole is stronger the bigger this purple is. And how do I decide how big it is? Just look at the molecular weight. The larger the molecular weight, the larger the atom or molecule is. Okay, and that's about it. The last one would be when I have two purple molecules where they both have to induce. This has got to do with just by chance. So if I look at a purple molecule and I were to take a picture of it, you know, with like a tiny little atomic camera, every microsecond or nanosecond or whatever, the charges inside kind of distribute and move around randomly. This is not very random, but imagine the red goes up, the blue goes down, and just kind of spins around over the place. Just by chance, there is a possibility that at some point the blue and the red will interface, like here in the third picture, and then it will be happy and it will have some sort of attractive force, just by chance. And when this happens, it will it will kind of like freeze in place for a minute, for a few seconds or for a minute, and it will form some sort of an attraction between the molecules, and then it will again disperse itself and do its own thing. But it still happens, and this is known as induced dipole. They induce their own dipoles, and it's very weak. It's a very weak force. It's also known as the London dispersion forces. So they're interchangeable. I'll often call them dispersion forces or London forces, usually dispersion forces. Or I'll just say induced dipole. These are the weakest of all intermolecular forces, but they're very prevalent because many things are not polar. Lots of oily things are not polar. And oil, if you take a look at oil, it's a liquid. So it's a liquid, and the forces that hold this liquid together are just induced dipole interactions. Okay. Again, the larger the purple, the stronger the interaction. So if I want to know if two molecules have a strong interaction and they're both non-polar, I just look at the molecular weight. So let's look at a whole bunch of examples. Now, before we do that, let's talk about hydrogen bonds, okay? This is a special case of this thing, dipole-dipole. That happens when hydrogen is present. If hydrogen is present in your molecule, like in HCl, okay, you might have hydrogen bonds. Not always. And HCl does not have hydrogen bonds. But hydrogen being present might cause an even stronger dipole-dipole interaction. Okay? We say that hydrogen likes to have fun, like fun. So if there's a molecule that has H and F, H and O, and H and N, they will have even stronger intermolecular forces than you would predict. So that's why water exists as a liquid, whereas it's very small. It's the molecular weight of 18. Other things that are that small, even if they're polar, do not exist as a liquid readily. Just so you're aware, these things also hold DNA molecules together, and they're responsible for the structure of DNA. Okay, so it's like a subclass of dipole-dipole. Okay, and it's even stronger than regular dipole-dipole, but it's still dipole-dipole. All right, let's look at, so this is an example of DNA here. For example, the DNA has an H and N here, and the other side has an O, and therefore they interact. So if H is bonded to an N in its native molecule, and it's seeing an O or an N or an F in another molecule, it will have hydrogen bonds. Okay, H2O again, if it is H in its native molecule, it is bonded to an H, O, or F. N, O, or F. And then in another molecule, it will be attracted to an F, O, or N. Okay, that's just the basics of hydrogen bonding. Okay, and a pretty quick chart if you want to test yourself to see which one is which. It's a pretty good chart to look at because I threw a whole bunch of different things at you. So you ask yourselves, do I have ions? Yeah, cool. Are there non-ionic things there too? Yes, so that would be ion dipole, so salt and water. There are no polar molecules, it's just salt, it's just a bunch of ions, so it's going to be just ionic bonding. Okay, and these are strong. These are the strongest. You can see on the rightmost. Okay, what if I have no ions at all? So these are all London dispersion, van der Waals forces, so actually in the bottom here, all van der Waals. Okay, do I have polar molecules? No, they're all not polar. If they're all not polar, I'll have dispersion forces only, like I just showed you, CH4, and also this Br2, Cl2, H2, a lot of other things. Do I have polar molecules? Yeah. Is there an H there? It's bonded to an FON? No, it's just regular dipole-dipole. Yes, it's hydrogen bonding. These are all van der Waals forces. They're missing here dipole-induced dipole, but I've shown it to you earlier too, and it would be between these two classes. Okay, so let's look at some examples now. Okay, let's look at this first. Arrange in order of increasing intermolecular forces, and I just showed you a chart with this. So I'll put the weakest as number 1 and the strongest as number 4, and I'll write here 1 is weakest and 4 is strongest. So we said that the strongest is ionic. Okay. The second strongest would be if I have dipoles and dipoles only, and it would be here. Then afterwards, if I have a dipole and an induced dipole, and then the weakest is if I have no dipole or ion at all. And this is also known as the dispersion forces. Okay, let's look at these molecules and let's try to classify their intermolecular forces. Okay, KBr, that's ionic, because this is an ionic compound, so it's just ionic. Okay. CCl4, if you look at back in the bonding chapter and this molecular geometry chapter, This guy looks like this. And it is tetrahedral. And it's symmetrical, and therefore this is not polar. So since this is not polar, okay, this has got to be, it has to induce a dipole in another CCl4. So these are both induced dipoles. This has got to be dispersion forces. This is the weakest. Strongest, the weakest. Okay. CO2. Again, if I look at my bonding chapter from before, it looks like this. It's a linear molecule, and it's symmetrical. Therefore, it's also not polar. Since it's not polar, we say that this is dispersion or induced dipole. Okay. CO, again, is going to be linear, like this, right? And CO molecules are polar because they have it's a linear molecule and it's not symmetrical. So what they do is they have poles, and we say that this is dipole. Okay. NH3 is, if you look at the again at that chapter, it would look like this. So it's trigonopyramidal, and therefore this thing is polar. And so since this is polar, it is not ionic, but it's polar. This is also dipole. Okay, and because it's got N and H, it's actually, I didn't ask for specifically, this one has hydrogen bonding. This one does not. So even though they're both dipole, okay, this one I would expect to be stronger than this. Methanol, again, it's, if you look at the molecule, it's going to be tetrahedral. I have H, and OH, but it's not symmetrical because I have this O here. So since it's not symmetrical, it's going to be also dipole. And because it has O and H, the H is bound to an O, it will also have hydrogen bonding. Okay, so that's that for that. Let's look at this. Let's try to actually quantify whether something is stronger or weaker. So I have CCl4 and CH4, CBr4, and CI4. These all have the following structure. C, and I'm going to call whatever's attached to them X. And it could be any one. It could be chlorine, bromine, hydrogen, or iodine. And these are tetrahedral as well. They all look like this. They're all not polar. All four are non-polar. All four are dispersion forces, or induced dipole. All four. Okay, so they all have very weak forces holding them together. And indeed, they're all gases. Okay, so how do I know which of these is the strongest? Well, we said that to increase dispersion, or to increase really anything, it's the higher molecular weight. So I'll just find the molecular weights for these things. Molecular weight. For CCl4, it's 154. This is 16. CBr4 is 332. And CI4 is 520. So I'll just say this is the strongest and this is the weakest. So I'll just organize them that way. CH4 followed by carbon tetrachloride, CBr4, and CI4. Okay, because they're increasing in size, and therefore they're increasing in intermolecular forces. Okay, so hopefully this makes sense. Okay, let's go back and discuss properties that are affected by intermolecular forces. And you will see these in a lot of upper classes, and this is the reason for all of this. And I will hopefully discuss some of these things more in detail as we go along. So, freezing point and boiling point, that's fairly simple. Okay, so I can ask you a question as, for example, which of these molecules has the higher freezing point? So the one that has the stronger intermolecular forces is going to be have a higher freezing point. Okay, and I'll discuss that in a minute. The red ones are the ones we're going to focus on the most, but other things are also affected by intermolecular forces. So when you take other classes, you might see elastic strength of materials, or hardness of materials, or conductivities, partition coefficients, diffusivities, a lot of different things that you see in other classes. You learn about them and you go through the motions of understanding them, but they have their basis rooted in intermolecular forces. Okay, and as I show you here, a lot of these are going to be which of these has a higher boiling point, which is a higher vapor pressure, whatever. And then hopefully you'll be able to do that. So I want to explain some of these things more in detail. I think everyone here sort of understands freezing point and boiling point. I'll discuss them a little bit later too. But the other ones may be a little more elusive.